Hello everyone, welcome to Sam Science View channel. This is the part 2 of that previous video. So now we have been seeing many crystallization processes. Today we'll start with the hydrothermal deposits. As the name implies, hydrothermal crystallization involves water and heat. As water percolates through the earth, it dissolves minerals just as it did with the sugar in your rock candy. Deep inside the earth, it meets with magma. Special fluids then escape from the magma that contain water, carbon dioxide, and volatile substances that give off gas. These hydrothermal fluids move through fractures in the crust. Along the way, they may dissolve minerals or combine with other groundwaters. These mineral rich fluids begin to cool in veins. With the right combination of temperature, pressure, time, and space, crystals are formed. Hydrothermal deposits are special because they can have combinations of elements not found elsewhere. One of the most important hydrothermal deposits of gemstones is the Muso Emerald field in Colombia. So you can see that emerald here. And the next one is the pegmatites. Magma in the upper part of the mantle sometimes becomes concentrated with volatiles. This volatile rich magma is sometimes forced into a cavity where it cools and becomes a pegmatite. Pegmatites differ from hydrothermal veins since magma acts as the primary agent instead of water. So you can see this pegmatites here. Next one is the environmental changes. Great stress exists inside the earth. Under the right conditions, temperature and pressure can rise to the point where existing minerals can't remain stable. This can cause minerals to change into different species without melting, which is known as metamorphism. There are two types of metamorphism, a contact and regional. Contact metamorphism occurs when magma forces its way into an existing rock formation. Under the intense heat, existing rocks begin to melt and eventually recrystallize as new species. These are stable at high temperatures. The regional metamorphism takes place on a much broader scale than contact metamorphism. It affects a much greater variety of minerals. Large pieces called continental plates make up the Earth's surface. They float on the mantle and on a geological time scale they move. However, they don't all move in the same direction. Some of them even compete for the same space. Where these huge structures are forced together, one is shoved underneath and the other is pushed up. This is how our planet's primary method for building mountains occur. Enormous compression forces exist where these land masses come together. This creates an area of intense heat and pressure. As the temperature approaches the melting point of rock, the minerals in the area become unstable. Over time, possibly millions of years, they change into new species. East Africa is an excellent example of an area of regional metamorphism. Some minerals found here don't exist anywhere else, such as tanzanite and commercial quality savarite. Now let's see how mineral species change. To understand some of the changes that occur to minerals during metamorphism, keep in mind what defines a mineral species, both its chemical formula and crystal structure. Sometimes during metamorphism, a mineral changes one of these properties but not the other. This still constitutes a change in species. Such changes create species known as polymorphs and pseudomorphs. Polymorphs are minerals that share the same chemistry but have different crystal structures. Polymorphous pairs of minerals are sometimes called dimorphs or dimorphous. For example, andalusite kyanite, and sillimanite all have the same chemistry, that is Al2SiO5. During metamorphism, they regularly polymorph into each other when their chemical ingredients recrystallize into new crystal structures. Thus, they change into different but polymorphous species. Pseudomorphs are minerals that change chemistry without changing their external crystal form. During metamorphism, some minerals may change chemistry but recrystallize in their customary crystal habits, showing no abnormal properties. However, sometimes a crystal will change chemistry without recrystallizing. These unique minerals are called pseudomorphs. A pseudomorph is an atom by atom replacement of one mineral for another without changing the original mineral's outward shape. Tiger's eye is a prime example of a pseudomorph. In this germs, quartz has replaced the original crocidolite, a form of asbestos, but they retain the fibrous structure of crocidolite. Marcasite can pseudomorph into pyrite, gypsum, fluorite, and goethite. So these are some of the pseudomorphs. Azurite frequently pseudomorphs into malachite, resulting in a perfect azurite crystal shape composed of malachite. So it's also a pseudomorph. When a mineral forms as a pseudomorph, it is described as the new mineral after the original. Thus, we might encounter pyrite after marcasite, gypsum after marcasite, malachite after azurite, etc. Next one is surface water. Rain plays an important role in recycling minerals. Erosion breaks down rocks and moves them to new locations. Once on the ground, rainwater is instrumental in new gem formation. Next one is the fossil formation. As water passes through the earth, it picks up chemicals that turn it into a weak acid. If heated or mixed with the right chemicals, it can become highly corrosive. This gives water the ability to dissolve even more minerals. As water percolates through the earth, it also picks up many ingredients. At times, it becomes too saturated to carry any more, so it leaves the excess in cracks and pores of existing rocks. This is how fossils and petrified wood are created. In other conditions, water encounters combinations of minerals that create a chemical reaction. The dissolved minerals are then deposited as new minerals in seams and cavities. This is how opal, turquoise, azurite, and malachite are being created. So, next one is opal formation. During the Cretaceous period, much of central Australia was covered by an inland sea. When it dried, it left the area layered with silica rich sands. For millions of years, rain has been dissolving the silica. During the hot, dry summers, the groundwater evaporates to the point where the remaining water can't hold the silica in suspension. The excess is deposited in seams and cavities not far below the surface. These silica deposits are called opal. The water-borne minerals can create the germ colors. Some gemstones get their color primarily from minerals essential to their chemical composition. For example, turquoise, azurite, and malachite all receive their color from copper brought by water. Copper-rich water must pass through limestone to create azurite or malachite. Turquoise also requires that water pick up some phosphorus along the way. So this is how they look like. Next is the germs formed in the Earth's mantle. Our knowledge of the Earth's mantle is still rather limited. However, the evidence shows that some gems actually form in the mantle. To do so, they need to crystallize at an extremely high temperature. The most notable examples of gems formed in the Earth's mantle are diamond and peridot. Oddly enough, both of these gems can also occur extraterrestrially. Both have been found in meteorites. Peridot gem formation from studying peridot deposits in Arizona. Geologists now believe some peridots were created on rocks floating in the mantle, approximately 20 to 55 miles below the surface. An explosive eruption brought them near the surface of the earth. Subsequently, weathering and erosion finally brought them close enough to the surface for people to find them. Next one is diamond gem formation, which is better understood nowadays. As mentioned before, most diamonds actually crystallize in the magma below the crust. However, the magma formations they are found in have a different chemical composition. They may come from greater depths, that is 110 to 150 miles below the surface. At this depth, the temperatures are higher and the magma is very fluid. This hot and fluid magma can force its way through the crust faster and more violently than other volcanic eruptions. During this process, it will break up and dissolve lower mantle rocks and then carry them to the surface. If the magma rose slower, the diamonds would probably not survive. The changing temperatures and pressure would cause them to vaporize or recrystallize as graphite. The speed of the magma rise may be so quick that the diamonds don't have time to transformation. So this is a small outlook picture of this, how the diamonds are formed, how diamonds reach the surface. A magma pocket comes in contact with the weak area in the crust, and then a quick explosion results, carrying diamond bearing magma to the surface. During the eruption, a cone builds on the surface. The carrot shaped pipe eventually cools, and then the cone quickly erodes away, geologically speaking, leaving the diamond bearing earth where the people can reach for it. Now, how mountain buildings and erosion bring gems to the surface. As we have just discussed about, a few types of gems come to the surface during volcanic eruptions. However, what about so many others that crystallize far underground? Most of these gems reach the surface through mountain buildings and erosion. Over vast periods of time, the movement of the continental plates causes mountains to rise. Then years of weathering take down the mountain, leaving the gem deposits near the surface. Of course, this process takes many millions of years. So you can see this picture, it may take many millions of years. So in conclusion, gemstones are precious and semi-precious stones that are highly valued for their beauty, rarity and durability. They are typically cut and polished to enhance their appearance and are used in jewelry, decorative objects, and various forms of art. Gemstones come in a wide variety of colors, shapes, and sizes and are formed from minerals or organic materials. Some of the most popular gemstones include diamonds, rubies, sapphires, emeralds, and pearls. These gemstones have been highly prized for centuries and are still highly sought after today. Other gemstones such as amethyst, aquamarine, garnet, topaz, and tourmaline are also highly valued and come in a wide range of colors. Gemstones can be classified as either precious or semi-precious. Precious gemstones are typically more rare and valuable and also includes diamonds, rubies, sapphires and emeralds. Semi-precious gemstones are more common and less valuable but can still be quite beautiful and are often used in jewelry and other decorative objects. The value of a gemstone is determined by a number of factors, including its color, clarity, cut, and carat weight. The color of a gemstone can range from deep reds to bright greens and can greatly affect its value. Clarity refers to the absence of inclusions or blemishes in the gemstone, while cut refers to the quality of the faceting and polishing of the stone. Carat weight refers to the size of the gemstone, with larger stones generally being more valuable. Gemstones have been used for centuries as symbols of wealth, power, and beauty. They have been used in jewelry, crowns, and other decorative objects and have been highly prized by royalty and the wealthy. Today, gemstones continue to be popular and are used in a wide variety of jewelry designs and other decorative objects. So it's all about the gemstones, how it is being created and how worth it is. So that's it for today's video. I hope so you got some scientific facts related to this, how gemstones are created. And if you have any doubts related to science, you can ask and get it rectified through this channel. We'll meet in the next video of the next Science Fact Treasury series. Until then, it's goodbye from Sam. Take care.